In this indeterminate problem, we're going to take a look at something that looks very similar to what we've done before, but two critical differences are going to happen. Before, when we looked at this problem, we had two concentrated loads, one at C, one at B, but now we only have one. And what's different is that at C, the material changes. So let's kind of get that in there. So aluminum over here at the right, steel here in the left. Right? And it may not look like it, but here's where we got to be really close. The shaft has two fixed ends, not one fixed and one free. So let's even just kind of do that. It has two fixed ends, so fixed here. And if we come over and look at that from a profile viewpoint, this is what we've got. Again, though, not constant material. Right? So we're going to go figure out what the resulting axial stresses are, and I'm going to make just a gigantic guess here about what I think the reactions might turn out to be, and then therefore a guess about what the answers might be. And so notice that the 70 kip load is not in the midpoint, so I don't think we're going to split the load effect evenly between the two ends. And this is a little bit like a simply supported beam. Put the concentrated load someplace, and if it's off center a little bit, more of it's going to go to the close support than the far support. And I'm going to use that as my rationale that 8 out of 18 of it goes to the softer side over here. That'd be 0.4444 times 70. Right? So that's going to be my guess. Is that, let's see, this is A over here, this is D. That I'm going to guess that RA is going to be equal to 31 kips acting to the right, because the load is acting to the left, and that would leave the balance over here at D. That would be 39 kips acting also to the right. Sum those up, that's 70 opposing it. Pure guess, just based on almost really determinate analysis rather than indeterminate analysis. It also leaves out some other things I can see right off the bat. For instance, it doesn't include that we have two different materials, and we'll just have to see how that all plays out. Now, with this indeterminate situation, what I'm going to do is again use a relaxation technique approach to this, and so I'm going to take the entire thing and I'm going to separate it out into two situations, both the same relaxed structure, determinate structure, but one with the actual load applied, and then one where we have the unknown reaction at A applied. Superpose those two together in the right way, and we'll get back to the original. Now, the right way is we got to accommodate that which we have relaxed, which is that in this primary system, we've relaxed the constraint that delta A doesn't move, that A is fixed. So under this condition, I think we can pretty reasonably predict that delta A is going to end up being a negative value going to the left if I take to the right positive for displacements. And then out here, of course, delta A will go, under condition of R, will go to the right. Right? And of course, which this is of course our compatibility equation, so let's write that down. And of course the condition under which we do that is that that's going to be 0. Now, this is kind of interesting. We can't forget that we have both steel and aluminum here, so it may not be quite as easy as what we might normally have done, but with just a single load. But notice the load is fortunately going to be happening right where the interface between the two materials is. So that makes it somewhat easier to play with, because delta AO in that case, which will always be the sum of what happens in segment CD plus what happens in CB under this primary condition plus what happens in AB in this primary condition, but those latter two are 0. They're just hanging out free in the air in the relaxed system. So it's only going to be equal to that one, and that one's going to be then much easier because that's just going to be the single compressive axial condition times, let's see, it's 8 feet long times 12 inches over 29,000 KSI for the steel, and the A is pi times r squared, cake r round, and so we get 70 times 8 times 12 divided by 2983 divided by pi divided by 0.75 inverse squared, and that's equal to a minus 0.131 inches, meaning it's going to the left. Compressive kind of effect, right? Now, because I'm going to use it later, I want to go back and get the EA over L, this NL over EA. You'll only understand why when I get to the very end, why I'm going to now do it that way. And that number, so that's 8 times 12 inches, or 96 inches. That's going to be 2983 times pi times 0.75 inverse squared divided by 96, and that's 533.8 kips per inch. Okay, now, again, you're not going to know why I did that until we get to the end. Well, let's find our displacement to get things put in back. That will only be in symbolic form, and it'll get a little kind of complicated. Complicated because we have two different materials. So we'll have a constant axial force in both, but we will have a, interesting, common axial force, but not common stiffness, because the material changes. So K, this is K for the steel, K for the aluminum in this case would be EA over the L for the aluminum, and that's 11,000 KSI is given to us, or we have to look it up knowing the specific steel, or rather aluminum. 0.75, same cross-sectional area over the length, which is ultimately here 10 feet long, or 120 inches. And that one, 11,000 times pi times 0.75 over squared divided by 120 is quite a bit less, 161.99, 162.0 kips per inch. Well, that's interesting. So note here, in this case, delta AR can be thought of in the following way. We have two springs that are in series. There's the K of the steel, there's the K of the aluminum, and we're tugging on it, pulling on it with an unknown value RA. And that total displacement that's happening out here, the delta AR, as that spring elongates, is going to be the sum of the elongation in the two segments. Right, so that's critical here. I don't know why I did that in black. That should have been blue. So we'll have the delta of the steel plus delta of the aluminum, and that's going to be equal to the axial force divided by the stiffness of the steel. That's the steel segment. And then the axial force, which is also RA, and stiffness of the aluminum. And we get this interesting thing here, that we get RA times 1 over K steel plus 1 over K AL, which we could say is RA divided by 1 over K equivalent, where the equivalent single spring constant for the whole system, the reciprocal of it, is the sum of the reciprocals of the individual ones. Right? And that's kind of an important result about springs in series that have a common axial force in them. Right? Now, mathematically here, we'll come back to that kind of concept later on, but mathematically then what we've got is RA times 1 over 533.8 plus 1 over 162.0. Right? Now, we can go through and find that equivalent number here, 162 plus 533.8 equals, that's the sum, divide by then these two multiplied, 533.8 and 162, and we get a real small number. If we take the reciprocal of that, that's 124.3, so equivalently that's RA over 124.3. If you're not sure about that math, just work that through. Another way to do that is 533.8, take the reciprocal, plus 162, take the reciprocal. That's this whole thing in the middle, take that reciprocal, and we're back to what that is. We could have represented it as a decimal times RA, but I just chose to do it that way. That gives me the equivalent spring stiffness here, which is not either one of the two values. It's not the average of the two. It's because it's in series that it turns out like that the whole system is actually more flexible. Interesting. Right? That over here, that over there, that plus that divided by all that. That's how that worked. Okay, so now that we have delta AR symbolically, we can then pull this together. We can find RA by going back to our compatibility equation way up here, way up there, that delta A equals delta AO plus delta AR, and delta A was 0. So, and delta AO was this minus 0.131. We take it to the other side, so it's a minus times a minus 0.131 inches is equal to then delta AR, which is RA over 124.3 kips per inch. And so when we take that over to the other side, we find out that RA is equal to 16.3 kips. Right? From a scale standpoint, then that sort of makes sense, right? It's smaller than 70. Now it's a lot smaller than what our guess was. That's pretty interesting. Our D will have to be the balance just from equilibrium. So that would be 53.7 kips. Notice I'm near the end, so I'm not keeping as many digits here and keeping a little bit more reasonable kind of numbers. And now if we want the stresses, we get the sigma in the steel is going to be equal to, well, the N over A of the steel and the axial force in the steel, of course, is going to be the same as that reaction at that left end, so that's 53.7 kips divided by pi times 0.75 inches squared, and that will be then 30.3, well, 30.4 KSI in compression for the steel. For the aluminum, then that will be N over A of the aluminum, and that's going to be then 16.3 kips over our same area, pi times 0.75 inches squared, and so I guess I'll do it this way, 16.3 divided by pi divided by 0.75 squared, and we get 9.2 KSI in tension. Should be, I know it says 9.22, but just call it 9.2 KSI in tension. That's, in both cases, are going to be less than the typical yield stress of steel and the typical yield stress of aluminum. So that's good. Now, one little final thing to go back to here. Why was it that this guess of proportionality turned out to be kind of far off, right? That the reaction at the left end would be 39, well, it turned out to be a lot more at 54. Up here, right there. And instead of 31, we ended up with 16. What was going on there? It has everything to do with stiffness, right? Relative stiffness here. Look at how much stiffer the steel was compared to what the aluminum. If we were to add up all that, 533.8 plus 162.0, we get total of 695.8. And if we take the 533.8 and divide it by that, you get 0.767, right? So 76.7% of the stiffness is over in the steel segment. Take that times 70, and you get 53.7. Bam! Right? This is where we come up with this idea that in indeterminate systems, the load effects or the stress effects are proportioned by relative stiffness. Right? In this, when we're isolating things down, how much of this load goes to each side? Well, how much stiffer is one segment compared to the other? That's how much is going to go over to that particular side. And that's where you get this sort of analogy with people, that the stiffer the personality, they tend to have more stress in their life. The more flexible your personality, the less stress you might have in life. On the other hand, stiffer systems have to accommodate less displacement and deformation. Right? If you're flexible, you start to become like seaweed, and you're going to have to be able to handle those large deformations. It's a yin and yang kind of thing, both structurally as well as, of course, in personalities.